All right, this evening's lesson is on perpendicular and angle bisectors. We're going to learn two theorems related to perpendicular bisectors and angle bisectors and their converses. So let's quickly review what a bisector is. In the picture at right, ray BD is the bisector of angle ABC. It is an angle bisector. It creates two equal angles, ABD and DBC are congruent angles. BD, if I said BD, I'd say BD bisects angle ABC. Right, true or false? Two perpendicular segments intersect to form four right angles. That is a true statement. And then finally, number 4, you can draw more than one line perpendicular to a given line through a point not on a line. That is false. There's only one line perpendicular to a given line through a point not on the line. Vocabulary, one of our words we've had from chapter 3 or 4, I don't remember which one. Equidistance means equal or distance, or related words equal or distance. Equidistance means at the equal distance from a single point or object. So if we look at our number line at right, circle 2 points equidistant from 0. There's actually two sets of points. There's A and D, and then there's B and C. Both of those are equidistant from 0. Name the points that are equidistant from the point C. That would be B and D. Using the diagram at right for exercises 7 to 8. Of course, that always gets in the way. All right. Circle 2 points equidistant from point Q. There are only 2 points that are equidistant from point Q. That is P and R. And we're going to name 4 segments that are equidistant from the origin. Here's the origin. And since it's a square or a rhombus, I guess it is, all sides are from the same distance. So it'd be segment PQ, segment QR, segment RS, and segment SP. So the first theorem we're going to learn about today is theorem 5.2, the perpendicular bisector theorem. Let's move that back down there in the corner. All right. Perpendicular bisector theorem says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if you look at the first diagram on the left, the hypothesis says if a point is on the perpendicular bisector of a segment, segment PM bisects segment AB, and AM is equal to MB. So therefore, the point P is on the perpendicular bisector. It is equidistant from the endpoints of the segment. So if I were to draw a line from PA and from PB, those two segments would be equal. So PA equals PB. So that's all theorem 5.2 says, that if I have a point on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. We also have the converse of the perpendicular bisector theorem, which basically says that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So it's just the opposite of what we had before. So looking at the diagram at right, point P is equidistant from R and T, which are the endpoints of the segment RT. So that means it's on the perpendicular bisector of RT. And so we would show that by our congruent signs and our right angle symbols. So that's how we complete the diagram at right to illustrate this theorem. So let's look at problem 1 and put this theorem to use. All right, look in the diagram at right. What is the length of segment QR? And we're given that PQ is 3n minus 1 and QR is 5n minus 7. So we have to solve for n. Now these are two segments that are equidistant, so that means they're equal. So segment QS is perpendicular bisector of PR, so Q is equidistant from P and R by the perpendicular bisector theorem. So the distance of PQ equals the distance of QR. So we say 3n minus 1 equals 5n minus 7. And now we're just going to solve for n. So once we get the problem set up right, the algebra is the easy part. So we're going to add 7 to both sides, and I get 3n plus 6 equals 5n. I'm going to subtract 3n from both sides, and I get 6 equals 2n. Divide by 2, and n equals 3. Now, I want to find the distance of QR. So the question originally asked, what is the length of QR? So we're not done once we find the value of n. We have to substitute n back into the equation and solve. So 5n minus 7, 5 times 3 minus 7, 15 minus 7 is 8. So the distance, the length of segment QR is 8. All right, so let's continue on looking at another problem using a perpendicular bisector. We have an amusement park. If the director of a park at the right wants a t-shirt stand built at a point equidistant from the spaceship chute and the roller coaster by the perpendicular bisector theorem, he can place the stand anywhere along line L. So this is line L, and if I put it anywhere on that line, it'll be the same distance between the two. Suppose the park director wants the t-shirt stand to be equidistant from the paddle boats and the spaceship chute also. What are the possible locations? So the first thing we have to do is we have to draw a line between the paddle boats and the spaceship chute. That's hard to say. So P to S. Now we want something equidistant between the two, so we're going to draw the perpendicular bisector of that line. And that's that line there. So any point on there would be equidistance between the paddle boats and the spaceship chute. So on the diagram, sketch the points that are equidistant from the paddle boats and the spaceship chute. We just did that when we drew these lines, so let's describe them. I'm going to put a point X. That's for the next slide, but just remember there's a point X there and go ahead and put it on your diagram. So the points on the perpendicular bisector of PS are the points that would be, went too far there real quick. Let's go back a slide. Those would be the points that are equidistant between the paddle boats and the spaceship chute. Now let's continue on. All right. Can you place a t-shirt stand so that it is equidistant from all three of these? And the answer is yes. And the way we do that is where I mark that X and you put an X on the previous drawing, that is the point where equidistance between the paddle boats, the spaceship chute, and the roller coaster. So that mark X. So here's how we say that. Place the stand at the intersection point X on the perpendicular bisectors of RS and PS. And by the perpendicular bisector theorem, XR equals XS and XS equals XP, so XR equals XS, which equals XP by the transitive property. So if you put it at point X, it'll be equidistant from all three objects. So there's when y'all say, how would you use this in real life? There's a real life example of how you would use the perpendicular bisector theorem. And remember, the distance from a point to a line is the length of the perpendicular segment from the point to the line. And this distance is also the length of the shortest segment from the point to the line. So just keep that in memory. Remember that, the shortest segment from the point to the line. Finally, let's look at another theorem for this chapter. It's the angle bisector theorem. It's theorems 5.4 and 5.5. The angle bisector theorem states, if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. So point S here is on the angle bisector, so the distance to P and the distance to R is the same. So if point S is on the angle bisector of PQR, then SP equals SR. The converse of the angle bisector theorem, if a point in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector. Point S is in the interior of triangle PQR, So SP equals SR, and S is on the angle bisector of PQR. So let's use the angle bisector theorem to solve a problem. We're going to justify our steps as we solve for X and solve for segment FB. FB is equal to FD, and that is the angle bisector theorem. So I can say 6x plus 3 equals 4x plus 9. And that's the distance of those segments in this particular instance. And that's just substitution. Now I'm going to subtract 3 from each side. I'm going to subtract 4x from each side, divide each side by 2, and I get FB, I get x equals 3. Now, FB equals 6x plus 3. That's given to me in the drawing. So I substitute my value of 3 in for x. I get 6 times 3 plus 3 equals 21. So we substitute 3 for x and simplify. So that's how we use the angle bisector theorem to solve a problem. Quick lesson tonight. So let's check over and make sure we understand exactly what we're doing. All right, use the figure it right. What is the relationship between AC and BD? So underline the correct word and symbol to complete each sentence. Segment AC is perpendicular to segment BD. AC divides BD into 2 congruent segments. BD divides AC into 2 non-congruent segments. So BD is not a perpendicular bisector of AC, but AC is a perpendicular bisector of BD. So we say AC is a perpendicular bisector of BD. Tomorrow when you come into class, we'll work on a worksheet for 5-2. Hopefully we'll all understand angle and perpendicular bisectors. And once we have finished that, we will work on our bridges for the remainder of the period. So I hope you have a good evening. Watch a lot of basketball tonight, but make sure you do your homework. See you tomorrow.